Thank you all for joining me here. I am Santosh, and the title of my presentation is Inverse Problems for Abstract Delay Differential Equations. And here are the outlines of my presentation. First of all, I will give the brief introduction about the terminology that I have used throughout my presentation. And after that, I will give my problem statement that I am going to discuss here, and then we will discuss the results related to this problem. After that, I will finish my presentation by giving some important references. So we all know that the first question that arises in our mind after hearing about the inverse problem theory is what is inverse problem basically. So inverse problems are opposite to the direct problems. Like in direct problem, what we have, we know the causes and the properties of the system, and our goal is to find out the resulting outcome or the behavior of the system. So this is our direct problem. But in the inverse problem, some of the internal properties or the causes of the systems are unknown to us, and our goal is to find out them by using some observed data or measurements. So this is our inverse problem. Like in this picture, we can see that in the forward or the direct problem, we know the input and we have to find out the output. But in the inverse problem, we have the observed output and we have to estimate the input so that we can get this output. So the next thing is the abstract differential equations. So abstract differential equations are basically those differential equations that are formulated in a functional analytic framework. There are many physical, biological, engineering problems that are modeled by the partial differential equations can be reformulated as an abstract differential equation in Banach or Hilbert spaces. So what this abstraction allows us to, in this abstraction, we suppress the space variable and our equation looks like an ordinary differential equation in the time variable in infinite dimension space. And we use the powerful tools like semigroup theory or cosine family and the resolvent family for the analysis of the solution for these kind of problems. So this whole process is called the abstract formulation, and the prototype of the problems that we get after doing this abstract formulation are known as the evolution equations. So, for example, let us consider an initial boundary value problem for the heat equation, which is given by this system 1 here, where this omega is a bounded domain in Rn with a smooth boundary. And let us denote that x of t as z of t dot, and x be the space of the functions on omega. For example, that is Lp omega. Then the derivatives dx by dt and del z by del t are both the limit of the same difference quotient, but the first limit is taken in the norm sense and second one is taken in the pointwise sense, because first one is the Freshlet derivative that we consider in abstract space, that is Banach space here, and the second one is the classical partial derivative. So to define the operator A, we take our space X as L2 omega, and the domain of A is taken as the intersection between these two Sobolev spaces H2 omega and H1 naught omega. And we have defined our operator A as AV is equals to this summation 1 to n del square V over del yi square, for V belongs to the domain of A. So now the abstract formulation of our partial differential system, that is equation 1, is given by this system 2 here. So here we can see that our partial differential equation has been converted into an ordinary differential equation. So, and the boundary condition here in equation 1 has been already involved with the domain of A. So from here, we can use the semigroup theory to analyze the solution of this problem second. So let me give the brief introduction about the semigroup theory and why we need this basically. So for that, let us consider the following Cauchy problem that is given by system 3, where A is a matrix of order n cross n, x is the state variable, state vector that is of order n cross 1, here x naught is the initial condition. Now we know that if n is equals to 1, then our matrix A will become a scalar, and the solution of these type of problems has the following representation, that is x naught exponent at. And if n is another finite number, strictly less than 1, and then in this case also, the solution will be given by this exponent ta x naught, which is a similar representation as for n is equals to 1. But here exponent ta is an exponential matrix which has the following series representation. So now the question arises, what if n is infinite, or we say that A is the unbounded operator. So now the question here is, like in the finite dimension case, do we will have the same type of generalization of the solution in this case also? And if such solution exists, then will it be the classical one or some of the other type? So this discussion leads us to the semigroup theory of the linear operators. And for more details, one can go through this book by Pesi Eman. So for that, what is semigroup? So let X be a Banach space and BLX denote the space of all bounded linear operators from the Banach space X to X. And a semigroup on X of the linear operators T of T is a function T from the positive real axis to BLX that satisfies these two conditions. And the second one is called the semigroup property here. So now if our semigroup T additionally satisfies this condition, then we say that our semigroup is a strongly continuous semigroup, or we say C-node semigroup. So for the analytic semigroup, so analytic semigroup is a C-node semigroup that can be extended from a real time T to the complex time, but inside a sector with the analytic time dependence on the time. In other words, we can say that C-node semigroup T is said to be the analytic semigroup if there exists an angle theta between 0 to pi by 2, such that the following conditions hold. So the next thing is the infinitesimal generator of the semigroups. Let T be the semigroup of the linear operators T of T. Then the domain of the generator is given by the collection of all those elements from the Banach space X for which the positive limit of this expression exists. And the infinitesimal generator of T of T the infinitesimal generator of the semigroup is the operator A, which is defined as the positive limit of this expression for all x belongs to the domain of A. So the next thing is the delay differential equation. We all know that the ordinary differential equations can't model the phenomena that happened in the past. Like if we have this type of ordinary differential equation, here we can see that there is no dependence on the past. But in the real life, there are many physical phenomena that involves the memory or delay effect in their formulation. Or we can say, for example, in ecology, delay differential equations plays a crucial role because they model the population where reproduction rate depends on the population size from the previous time period. So for the mathematical things, delay differential equations are a class of differential equations that involves the delay or memory effect in their formulation. For example, this x prime t is given as f of t, xt minus tau 1 and so on. Here tau j are called the delay terms here. If this tau j are the constants, then we say that this is our constant delay differential equation. But if they depends on time, then we say that is time dependent delay differential equation. And if further it depends on the state vector as well, then we say that it is called the state dependent delay differential equations. So this is the problem statement that I am going to discuss here. Let X be the reflexive Banach space, and we have considered the following degenerate identification problem with the delay arguments, which is given by the system 4 and 5, where this M and L are the closed linear operators with domain of L is contained in domain of M. U is the unknown function that we have to find out. F is the given non-linear function that is ellipsis continuous in the second variable. This omega is the initial history valued function, and this is the additional condition that we have to use to find out this unknown parameter. So here this psi is the continuous linear functional from the Banach space X to R. H and G are the given real valued functions that are defined in some suitable spaces. So here our goal is to find out the unknown parameter U along with this solution Y by using this additional condition which is given by this equation 5 here. So these are the terms that I already introduced to you. Here, this H and G are in C1 plus alpha spaces, where the C alpha is a set of all Holder continuous functions with exponent alpha, and C1 plus alpha is the collection of all those continuously differentiable functions whose first time derivative is Holder continuous with exponent alpha. So here is the overview of my problem. I have considered the first order identification problem with the delay arguments in the Banach space, and we have discussed both the degenerate and mainly the non-degenerate and mainly the degenerate case. So firstly, we have discussed the existence and uniqueness of the solution for the non-degenerate case. And then for the degenerate case, what we have done, we have converted our degenerate problem to the non-degenerate one, and then with the help of the results obtained in the non-degenerate case, we have found the existence uniqueness of the solution of this degenerate problem. At last, some of the application to the partial differential equations are given to validate this abstract approach. Yeah, so for the non-degenerate case, we have considered the following problem that is given by system 7 to 8. Here A is the minus A is the generator of the analytic semigroup and u is the unknown function that we have to find out. F is again the given function that is ellipsis continuous in the second variable. This is the initial history valued function, and this is the initial condition that we have to use to find out this unknown function along with y. So we have to find out the pair u and y such that this compatibility condition holds along with this 7 and 8. And these are the terms that I already told. So let minus a be the infinitesimal generator of the analytic semigroup, and this omega is the continuous function from minus lambda to 0 to x, and f is the ellipsis continuous function in the second variable. Then a continuous function y is said to be the mild solution in this interval if it satisfies the following integral equation. So here is the theorem for the existence in uniqueness of the solution for the non-degenerate case. So here the psi with a continuous linear functional from x to r, and this omega t and f of t lies in this interpolation space, which is defined as this, where minus a represents a generator of the bounded analytic semigroup, and h is in the c1 plus alpha, g is in c1 plus alpha space, and if this condition, this non-singularity condition hold, then we say that our non-degenerate problem has a unique solution which is given by this pair. So to prove this, what we have done, we have applied this additional condition that is given to us to our original equation, and then by using that condition we have the following relation. Now this is given assuming that the psi of f is non-zero, then we can rewrite this equation for u of t, which is given by this equation 11. And if we put this that value of u in the mild solution of the problem, then we have the following relation, which is given by this equation 12 here. Now applying both side a, we have the following equation, this equation 13, and we have denote this a by t by x of t. Then our equation 11 and 13, that is our unknown parameter that, along with this mild solution, is given by this equation 14 and 15. So here we have introduced the operator S as this, and then our equation 15, that is our this equation, can be rewritten as in this form, this equation 16, where I is given by this operator here. So now here we have to now to prove that equation 16 has a unique solution, we have to prove that this series converges. So for that we have the following estimate for this operator S, and then further continuing for the S square t, we have this estimate, and by the mathematical induction we have the estimate for the S raised to the power n. So from here we can see that S raised to the power n is a contraction for sufficiently large n, and this is a domain of a valued function along with this sigma t omega t. So we will have the solution that exists uniquely by using the Banach fixed point theorem, that our non-degenerate system has a unique strict solution, but we want the maximal regularity of the solution of x, which is given by this ay. And for this we need some additional conditions, and this consider equation 15, which was our mild solution. And note that this condition, this exponent minus ta a omega 0 will be in the Holder continuous space if and only if this a is omega 0 will be in this interpolation space. Yeah, moreover, if H is in this C1 1 plus alpha and this AF is in this interpolation space, then this convolution term will be in this C alpha space. And so therefore, if we have these properties, then our solution x of t will be in C alpha space, and this x of t is given by this ay. So ay will be in this C alpha, which implies that a u will be in C alpha. So there exists a solution. This is given by this pair, which exists uniquely. So for the degenerate case, we have assumed that M and L satisfies the following condition, which is given by this equation 18, or we can rewrite this equation as this equation 19 here, where T is the operator which is given by ML inverse, because L was the operator that was invertible, but M may not be the invertible. So this is because of this M may not be invertible, we have the degeneracy in this system. So let us denote Ly is equals to x, and observe that T is equals to ML inverse is a boundary linear operator from x to x. Then the system 4 to 5, that was our original degenerate system, can be rewritten as this system 20 to 21. And now since the inequality 18, which was our estimate for the operators M and L, holds and X is a reflexive Banach space, then we can represent X as a direct sum of the null space of T and the closure of the range space of T. So here we have defined an operator T tilde, that is the restriction of the operator T onto the closure of the range space of T, which is a bijective function, and it implies that minus of T tilde inverse generate an analytic semigroup on R of T. On the close, yeah, there is a typo, so there would be the range space, closure of the range space of T. Let P denotes the projection along the closure of range space of T onto N of T. And so here let ML be the two closed linear operators in the reflexive Banach space X with this L to be invertible and bounded. This psi is in X star, which is the dual space of X. G is in C1 plus alpha. H is also in C1 plus alpha. And suppose the condition 6, that is our compatibility condition. And this equation 18 is nothing but the estimates for the operators M and L. And then if we will have the following relation, that is this non-singularity condition and this estimate, where this V1 and V2 are given by these, then the problem 4 to 5, that is our degenerate problem, will have the unique solution which is given by this pair. So to prove that, we have given that P represents the projection onto the null space of T in the direction of RT closure. So now using the properties of the projection operator, we can see that our system 2021, that is, yeah, this system is equivalent to the system, this T tilde I minus P, there I is the identity operator, P is the projection operator here, which is given by this 22 and 23. So we have defined a new variable W, which is given by this T tilde I minus Px. So from here, X and this I minus Px will be T tilde inverse W, so that the system converted into this non-degenerate system. So from here we can see that there is no degeneracy, and this T tilde inverse generates the analytic semigroup. Minus of T tilde inverse generates the analytic semigroup. So by using the results that were proved in the first theorem for the non-degenerate, we had the following conditions, and then by using that procedure we can easily find out the pair or the solution for this problem, which is given by this pair. So now our next objective is to relax the assumptions. Like in the first case, we have taken the more regularity of the functions that we have considered in our problem. So here we want to relax the regularity, and then we will see that what will happen. So for here we have taken that minus a generates the analytic semigroup of the negative type, and this, but we take this sigma t is in the interpolation space, and this f is in this interpolation space, where this alpha naught is a new parameter which is lies between this alpha and 1, and our goal is to find out again this pair y and u with ay is in C alpha, such that our system hold under this compatibility condition. So let us consider that minus a as a generator of the analytic semigroup in X of the positive type, and this H is in C1 plus alpha space, this sigma T is in this interpolation space, this F is in this interpolation for this alpha naught exponent, and where this alpha naught lies between this alpha and 1. And if in addition 9 holds, 9 is our compatibility condition, and this non-singularity condition holds, then the problem 7 to 8, that was our non-degenerate problem, will have the solution that exists uniquely. So here we can see that the equation 13, that we have applied operator A on the mild solution on the both side, which is given by this equation 27. So we have defined a variable x of t that is given by a y of t. So we have the following relation, which is given by this equation 28. And let us introduce the operator s here, which is given by this. So from here we can see that in the previous case, we have assumed that f is only in the d alpha plus 1. Yeah, dA alpha plus 1 space. So there was, so from there we can see that this integral is well defined. So, but here in this case also we have the following estimate for this term. So from here we can get this estimate for this SWT, and further doing the calculation for the S square, and by using this beta function we had the estimate for this s square w and s cube w, and by doing the mathematical induction we have the following estimate for the s and wt. For from here we can see that this gamma and alpha naught tends to infinity as n tends to infinity. So again here this the spectral radius for the operator s will be 0, and again that it is given that f is in this interpolation space and h is in c1 plus alpha, or we can say h prime is in c alpha. Then we can deduct from this lemma 3.304, 4 is given by this article, that the convolution will be in this C alpha space. And so from the our previous theorem, if these conditions holds, then the following equation will have the unique solution but in the continuous space. So if we want the more regularity of the solution, and we have to make use, so we have some additional conditions. So for that we introduce the subsequent LP space that are associated with the given positive constant beta, which is given by this set, and equipped with the corresponding norm, which is defined as this. Furthermore, the norm of H in this space is given by this here. And so from here, we have the following estimate for this convolution term. And so by choosing beta suitably large, and recall that I was the operator that x is equals to s of x of t plus I is in C alpha space, then the norm of the operator s is less than 1. So we say that S is a contraction map. So by using the Banach fixed point theorem, we can say that the solution exists uniquely. And we are here that we have X as the is equals to AY, have the desired regularity of the C alpha. Yeah, so this is the similar kind of theorem for the degenerate case also, as we have seen that we have converted our degenerate problem into the non-degenerate one, and then with the help of the non-degenerate case we have find out the solution for the degenerate case. So if we have proved the theorem 7, the previous theorem that I have already discussed, and we have additionally these conditions for the degenerate case, then we will have the unique solution for this case also. So here I have considered as an example in which I have considered an identification problem for the Poisson heat equation with the finite delay within the bounded domain region this Ohm in Rn, where n is greater than or equal to 1, and this region has a smooth boundary which is denoted as del Ohm. So we have the following identification problem. Here this m may not be invertible, and this delta is the Laplacian operator here. U is the unknown function that we have to find out. This is the boundary condition, and this is the initial history valued function. And this is the overdetermined condition, or we say that the additional condition that we have to use to find out this unknown parameter u along with this y. So these are the terms that I already introduced to you. So for that, here we have taken our space is that Sobolev space HK omega, which is defined as this, and the Sobolev space with the compact support is given by this set, where this del Ohm is the boundary of Ohm, and the space H inverse Ohm is the Sobolev space that represents the dual of the Sobolev space H1 Ohm. So to represent our inverse problem that we have considered for that partial differential equation into an abstract form, we have defined the following operator, that m is given by this my is equals to m small my, and this L is given by this minus Laplacian of y, with the domain of m and L is given by this Sobolev space H1 naught omega, and we have the following representation of the variables or the parameters that we have taken, that yt, this j is, so that here we can see that we have suppressed the space variable, and we will consider only this y of t, and similar for all other things. And for that we have the following abstract formulation of our considered partial differential model. So here we can see that this problem looks exactly like we have considered as a degenerate case in our original problem. So by using those approaches or the conditions that we have already discussed in the results, we can easily find out the solution. And we have, so from here we can see that all the conditions of the theorem 8 can be applied. And if we have these conditions, so from here we can see that our problem 3031, that was our partial differential model, has a unique solution which is given by this pair. Yeah, these are the references that I have used in the terminology. So that's all from my side. Thank you so much for your kind attention.